Good morning. I am Neil Sana, Group 7, Team Wireless Sampayan. And this is my group mate, Maravilla. So we made this report today. So let me explain about evolutionary algorithm. So let's start with the definition. So evolutionary algorithm is a subset of an evolutionary computation, a generic population-based meta-horistic computation algorithm. This mechanism is inspired by biological evolution, such as reproduction, mutation, recombinations, and selections, often perform well, approximating solutions to all types of problems because they ideally do not make any assumptions about the underlying fitness landscapes. Next, evolutionary algorithm. Evolutionary algorithm, or we call it is also called as EA, short term, has been very important in the last decade. It's also evolutionary algorithms are set of modern methods, heuristics used usually successfully in many applications with great complexity. Its success on solving difficult problems has been the engine of a field known as evolutionary computation, or the EC. So how does it implement? So step 1, it generates the initial populations of the individuals randomly. First generation. It's the first generation. Step 2, evaluate the fitness of each individual in the population. Example, the time limit, sufficient fitness achieved, and etc. Step 3, repeat the following generalization steps until termination. So this is the steps. This is the steps in steps 3. So first, select the base fit individuals for reproduction, parents. Breed new individuals through crossovers and mutations operations to give birth to offspring. Next, it evaluates the individual fitness of new individuals. For the fourth time, it replaces this fit population with new individuals. So next. So evolutionary computation, what are the benefits of it? So in EA and EC, there's also benefits on it. So using EC techniques mostly came from flexibility gains. Their fitness to the their fitness to the object target in combination with a robust behavior. Nowadays, EC is considered as the adaptable concept for problem solutions, especially complex computation problems. This vision is the alternative to some old discussion that shows EC as a collection of similar algorithms ready to be used in any problem. So this is the location of different families of evolutionary algorithm. So later, I'll explain the different types of evolutionary algorithm. So first is a computational intelligence. Then there is an evolutionary computation, neural networks, and fuzzy logic. So in evolutionary computation, there is GA, EP, ES, GP, and CS. I'll explain it later. So most of the present implementation came from any of these three basic types, strongly related through although independently developed. Genetic algorithm, which is the GA. Evolutionary programming is the EP. Evolution strategies is ES. Two groups of EA became very important. The GP, which is the genetic programming with a lot of real problems, and the CS is the classification systems used for machine learning and for discovering rules in rules-based system in RBS. So next. So this is the types was inside the which is inside the evolutionary computation. So this is the types of evolutionary computation. So first, the genetic algorithm. So this is the most popular type of EA, evolutionary algorithm. 1/6 the solutions of the 1/6 the solution of the problem in the form of strings of numbers. Additionally, binary, although the best representation are usually those that reflect something about the problem being solved. Next is the genetic programming. So here the solutions are in the form of computer programs, and their fitness is determined by their ability to solve the computational problem. So next is the evolutionary programming. Similar to genetic programming, but the structure of the program is fixed and it is numerically parameters are allowed to evolve. Next is the gene expressions programming. Like the genetic programming, GEP, which is the genetic expression programming, also involves computer programs, but it explores a genotype phenotype system. So next is the evolution strategy. Works with vectors of real numbers as representations of solutions, and typically use self-adaptive mutations rates. Next is the learning classifier system, or the CS, which a while ago is classification system. So here the solution is a set of classifiers rules, means that rules of conditions. Michigan LCS evolves at the level of individual classifiers, whereas at Pittsburgh LCS uses population of classifier sets. Next. So this is the example of a family generic test methods. So EA are populations based. So example, they process as a whole collection of candidates solutions simultaneously. EA mostly use recombination to mix information or more candidate solutions into a new one. EA are stochastics. Okay, next. Okay, components of evolutionary algorithm. It consists of a representation, evaluation function, population, parent selection mechanisms, variations of operators, recombinations, and mutations. Survivor selection mechanism, and also the survivor selection mechanism. So EA have number of components, procedures, or operators that must be specified in order to define a particular EA. Next. So the characteristics of EAs are flexible, this is applicable to different problems. Robust, can deal with noise and uncertainty. Adaptive, can deal with dynamic environments. Autonomous, without human interventions. Decentralized, without a central authority. Okay. This is an example. So it's an infinite monkey theorem. So given enough time of hypothetical chimpanzees typing a random word as a part of its output, almost surely produce all Shakespeare's play. Okay. So what is the particular theorem? The probability of the monkey exactly typing a complete work such as Shakespeare's Hamlet is so tiny that the chance of its occurring during a period of time of the order of the age of the universe is minuscule but not zero. Example: typing banana. The typewriter has a 50 keys. Probability of each letter to be typed right is 1 by 5. So the zero probability of that banana is typed right is 1 over 5 raised to 6, equals to less than a 1 in a billion expected of number of trials to write banana is equals to 15 billion. So monkeys, typewriter, and evolutionary. So evolution being randomized, generate, and test process present some similarities to the monkey with the typewriter process. However, natural selection can produce unlikely results. Could a monkey accidentally type helmet line? Matt thinks it is like a whistle. The chances are virtually zero. So next example is the evolutionary art, or the Mona Lisa. So we all know about the Mona Lisa evolution. So wait. Okay. So Mona Lisa is one of the famous paintings. So the problem for this is paint a replica of Mona Lisa using only 50 semi-transparent polygons. So as you can see, there's a polygon here. Hindi masyadong kita, but it is made of 50 semi-transparent polygons, and it became Mona Lisa. So let's proceed. So evolutionary art, Mona Lisa evolutions. A candidate solution is a set of 50 transparent polygons of various colors on the canvas. So representations for each polygons. There is a real vectors describing the shape of the location and the color of the polygon fitness to minimize some of the difference in color on components, or the RGB, on each pixel between the phenotype and the target image. Next, it is a standard of crossover and mutation on real vectors. So that is the Mona Lisa evolutionary art. Okay, next. So this is this structure design example. So it's a car evolution. So the problem of the car using a polygon and wheels able to run on a terrain. So this is the car evolution, which are using polygons and wheels to run. Okay, next. So this is the structure design of the car evolution. So a candidate solution is a set of polygons connected in a central point and wheels attached to them. Representation for each polygon. There is a real vector, a gene describing the shape of the polygon for each wheel. There is a value specifying its edges, and it is the location of its center. The fitness. How far can the car goes on the terrain when run? The mutation crossover, a variation on mutation and crossover for real vectors. Okay, I'm back. Yes. Next example is the ant controller. So this is the diagram. Is an example of ant controller. So it is the Santa Fe trial problem. So find a program that controls an ant able to eat all the food petals on the trail. So this is the example. So next. So the ant controller. So its candidate solutions sets of instructions. So from left, right, move, food ahead, program 2, program 3. Those are the examples of the set of instructions. So it is a fitness to maximize food eaten. So control program can be represented as trees, mutations and crossovers acting on trees. So give me the answer. So this is the answer. So this is the parent A, the parent B, the child A and child B. This is the crossover, which medyo malabo po yung picture, pero the crossover from here to this one and this one to this one. So this is example of the uncontroller with the Santa Fe trial problem. So next is the traveling salesman problem. So this is the example of a map which is from Berlin. So given a list of cities and their pairwise distance. The task is to find a shortest possible tour that visits each city exactly once. So in Tagalog, hanap siya ng pinakamaiksing road para lang maka visit sa isang beses, isang city. Okay, traveling sales problem. So a solution is to tour passing through all cities. Represents as permutations, list of integers without representations. Example: 2, 5, 1, 4, 3 for a tour of 5 cities. So fitness to minimize the tour length search operators. So 1 point crossover for permutations. Part of each parent is copied and the rest is taken in the same order. As in order, second parent swap mutation, 2 elements are swapped at a random. The offspring is valid permutation. So example, parent 1 is 12, 2, 3, 1, 4, 5, and the O is 1, 2, 3, 4, 5, 4, and the M is the 4, 3, 5, 2. Then the parent 2 is a 2, 5, 1, 4, 3. So next. So it is the symbolic regression. So find a curve that best fits given noisy data points. Okay, this is the example of the regression. So the candidate solutions are curve. Example: functions like y is equals to sine x times 2 plus 1. Fitness to minimize sum of errors at each data point. So functions can be represented using tree encoding. So plus, minus, times 2 points. So this is the example and the solution of it, given the diagram below. So next. So search operators, sub-tree swaps crossovers. Wait. Swap 2 subtrees in parents. Sub-tree mutation, replace a subtree with a randomly generated subtree. The offspring is valid function. So this is subtree. So parents to offspring. Okay, this is the crossover point. This is the crossover point also. So this is the equation given a while ago, and it was search operators. Next. So that's only the example that I reported. So I'll show you a short video, a 2 short video, to deeply understand what is the evolutionary algorithm.
Step generation to see what's going on behind the scenes with every generation that happens. Here is our first creature! It's got just for 2.5 years. In January 2013, I started working on an evolution simulator, but I never finished it. The simulator lay dormant for 2.5 years. Until now! Just this week I have resurrected it, and it's time to see the almost finished product! Since there are no creatures yet, create 1,000 creatures. They will be randomly created and also very simple. Wait, before we get started, I should tell you what a creature is. Every creature has an internal clock, like a heartbeat, except that it never changes speed throughout the creature's life. This is a node. Nodes can vary in friction, from white being very low friction to black being very high friction. Nodes collide with the ground, but they don't collide with each other. 2 nodes can be connected with a muscle. Muscles have many more traits than nodes. They have an extended length and a contracted length. They also have an extended time and a contracted time, which are based off of the internal clock. Finally, muscles have strength. Basically, a muscle is rarely exactly the length it's trying to be. It's always trying to push or pull its 2 nodes so that it reaches its target length. How hard can it push or pull? That's its strength. The higher a muscle's strength is, the more opaque it appears. Okay, so who gets to determine all these traits, like how frictiony nodes are, or what muscles' contract times are? Well, at the beginning, it's just random chance. They're randomly generated. So here are our 1000 randomly generated creatures. Their goal is to run as far as possible to the right in 15 seconds. They don't know that yet, but it's true. To start off, let's do a step-by-step generation to see what's going on behind the scenes with every generation that happens. Here's our first creature! It's got just 15 seconds to prove how well it can move to the right, but it's not doing very well. It's just getting up and then collapsing and then getting up and collapsing. I mean, it is going right, which was the goal, but it's not going very fast. 0.86 meters, can the next creature do any better? Unfortunately, when all nodes hit the ground at the same time, that's pretty much it for the creature, because at that point, there's really nothing to push or pull against, so the creature just can't move anymore. So this collapsed triangle gets a measly -9 millimeters. We're going to speed up the playback rate now so we can get through all 1000 creatures in time. Also, look how symmetrical this creature is! But it still moved backward. Our fourth creature has what looks like a sail sticking up in front, but it's not catching any wind. Because these creatures were randomly generated, I think it's fair to say that about half will go left and about half will go right. That is, if you don't count the ones that don't move at all. Oh, I forgot to mention that a creature's position is determined by the average position of their nodes. So a creature can't just fling one of its nodes really far forward and get an unfair advantage that way. Now we've seen 10% of the creatures, but don't worry, it's gonna speed up really fast from here. All 1000 creatures have been tested. You can see creature 1 in the upper left. That's the one that kept collapsing and getting up again. And here's the rest of the first 4. Well, anyway, let's sort them all, from fastest to slowest. Going backward is considered very slow. Here's our first creature. Despite all of its stumblings, it still managed to rank 26th out of 1000, which puts it in the top 3%. I guess it's not hard to do well when your competition is all randomly generated. Creature 195 managed to do the best out of all 1000, traveling almost 2 meters in just 15 seconds. Just watching it though, you can tell that improvements can be made. Who was the slowest creature? Well, that's creature number 331, who traveled even further than the fastest creature, but backwards. Okay, let's kill the 500 slowest creatures. Boop! To be specific, there's a slight gradient allowing some lucky slow creatures to survive, and some unlucky fast creatures to die. But overall, the faster you are, the more likely you are to survive. Hooray for creature 1, who, as expected, survived, and gets to pass on their genes. Creature 2 and 3 died though, they were too slow. And creature 4, right around the middle, survived also. As we reproduce, you can see how the gene pool slightly improved due to this killing of the slow and spreading of the fast. Also, the new offspring are slightly mutated from their parents. Again, randomly. Nodes might become more or less frictiony, and muscles might gain or lose strength. Less frequently, bigger changes will happen, such as losing or gaining nodes or muscles entirely. But those are rare and again are determined randomly. Reproduction here is asexual, so there's no mixing of the genes. I know that could be a major setback for the creatures, but I'm sure they'll still get by fine.
Okay, so hi, so that was the first algorithm simulator. So you can continue it using just type evolutionary simulator. Though there's a part
in January 2013,
four parts. So there's a 4 parts. So just continue if you want to continue this video. But that's a intro. So next, I also give you a genetic algorithm which is connected to evolutionary. Is connected to evolutionary algorithm. So let's play the video.
Nowadays, scientists and engineers have huge volumes of information at their fingertips. Whilst this is extremely beneficial, it has its problems. Nowadays, scientists and engineers have huge volumes of information at their fingertips. Whilst this is extremely beneficial, it has its problems. When there are questions to be answered, how can they find the solutions amongst all of the data? The old approach would be to search through it all. The new approach is an evolutionary algorithm. An algorithm is a list of step-by-step instructions for the computer to solve problems. This algorithm is used to improve a variety of things, from fuel efficiency in airplanes to trading strategies. For example, with airplanes, evolutionary algorithm optimizes the shape, minimizes wind weight, and maximizes fuel weight to improve the overall efficiency of the airplane. This algorithm is based on evolution in nature and is a fast way to find a good solution without checking every possibility. To show how this algorithm works, let's say we want our computer to generate a creature which can walk the furthest. First, an initial population is randomly generated. Each individual has its own characteristics. We make the creatures walk and calculate the distance traveled for each of them. We then randomly select two creatures that perform well, generating a new creature. In the mating process, the child gets some characteristics from one parent and some from the other. A random mutation occurs, which slightly changes some of these characteristics. Using this process with several creatures, the next generation is created. The whole process is repeated multiple times. After each generation, the average distance traveled increases because good characteristics are becoming more common. The evolution stops when there is no significant increase in average distance traveled by the creatures between two generations. We can assume that the optimal solution is found. In conclusion, although evolutionary algorithm doesn't check every possibility, it's a fast way to find a very good solution to problems with a lot of data.
Okay, that's the example of genetic algorithm. So I'll give one more example and last. Right. So my next example is a genetic algorithm for a 3D car made in utility. So I'll show you another video. This is the last video. So okay, let's play it. I hope you're listening. the video of a 3D card made utility using the genetic algorithm. So I hope you enjoyed my reporting. We are the Group 7, so we report about the evolutionary algorithm. So this is Neil Sana, and this is Kino Maravilla. I hope you enjoyed our video. Thank you so much.